Hello and welcome back to the class number 18 on principles of polymer synthesis. We had been talking about chain copolymerization, and at present we are talking about the ideal copolymerization system where the reactivity ratio, the multiplication is equals to 1, and we directly go back to the graph in the slide from which we were talking in the previous class. So, as we told that if we have the monomer reactivity ratios very different, it becomes very difficult to produce a polymer that has appreciable amount of the less reactive monomer, irrespective of what is the composition of the co-monomer mixture. So, if you put lot of less reactive monomer in the co-monomer mixture, still a less amount of that will go into the copolymer, because the other monomer is highly reactive. So, you can already see that this is the mole fraction of monomer 1 in the co-monomer feed, which is quite low, but correspondingly say let us here if you look at it is, so say 0.2 is the mole fraction of monomer 1 in co-monomer feed, let us say. So, correspondingly what will be the mole fraction of monomer 1 in the copolymer that has been produced? That will be close to 78 or 80%. So, it will be close to 80 mole percent, even though you have only 20 mole percent of the monomer 1 and around 80 mole percent of monomer 2 present in the starting co-monomer mixture. The copolymer composition will show you around 80 mole percent of it is only monomer 1 and rest is monomer 2. So, this is what is given by the graph, and correspondingly if you see this particular graph, if your monomer 1 R1 value is 0.1. So, even if you have say for example 60%, say 60 mole percent or 0.6 mole fraction, say 60 mole percent of the co-monomer feed is only monomer M1, that means rest of that is 40 mole percent is your monomer M2, still less than 20 mole percent will go into the copolymer composition. So, that is the situation that we were talking about. Now, let us do a small problem in order to have more understanding of this particular situation. So, let us say your R1 is 10 just like that graph and R2 is 0.1, and let us say the co-monomer feed composition is given by this, F2 is 0.8. So, that means 80 mole percent of the co-monomer feed is composed of monomer 2, which is the less reactive monomer. So, I just want to show you that even if you are taking a lot of monomer 2 in the co-monomer mixture, you will get very less amount of monomer 2 correspondingly even with this value into the copolymer, because of this discrepancy in the reactivity ratios of the monomer 1 and monomer 2. So, monomer 1 will overwhelmingly go into the copolymer and it will have more preference to go into the copolymer than monomer 2. So, what is, so then the question is what is the instantaneous copolymer composition? This is the question. So, when your R1 and R2 this multiplication is 1, then the expression of F1, which is nothing but R1 F1 square plus F1 F2 divided by R1 F1 square plus 2 F1 F2 plus R2 F2 square, this basically reduces to a more simplified form R1 F1 divided by R1 F1 plus F2. You can just work it out by putting R1 R2 equals to 1. So, if you put the values here, R1 is 10, F1 is 0.2 because F2 is 0.8, total is 1 mole fraction. So, this is 0.2 divided by R1 is 10, F1 is 0.2 plus F2 is 0.8. So, I have already worked it out. So, I will just write it down here. So, you will get 71.4 mole percent of monomer 1 into the copolymer, and F2 is 1 minus F1, which will be around 28.5 mole percent. So, the copolymer, what will be the instantaneous composition of the copolymer? 71.4 mole percent of the copolymer in the copolymer, if you take the 100 as the basis. So, 71.4% will be your monomer 1 present in the copolymer and 28.5% will be monomer 2 present in the copolymer, even though in the co-monomer feed mixture you had taken 80 mole percent of monomer 2, only 28.5 mole percent is present in the copolymer because of this overwhelming difference in the values of R1 and R2. I hope this particular problem has illustrated the concept that I wanted to tell you, that I wanted to elaborate upon. So, now we go into what we call as alternating copolymerization. Now, alternating copolymerization will occur when R1 R2 this multiplication is equals to 0, which means M1 star will add M2 with a overwhelming preference over M1, and M2 star will add M1 with a overwhelming preference over M2. That means, after M2 only M1 will come, and after M1 only M2 will come. So, ultimately it will be alternating M1 M2, M1 M2, M1 M2, the same way M2 after M2 only M1 will come, M2 M1, M2 M1, M2 M1. So, it will be alternating. So, that kind of situation is the extreme alternating behavior, and that happens only when R1 equals to 0 and R2 equals to 0, but in other situations where R1 and R2 both are small less than 1 and the multiplication is close to 0, then you will get what you call as moderate alternating behavior, that it tends to alteration. So, the copolymer composition tends to alteration, but it is not a perfectly alternating scenario. So, let us go into the graph in the slide to explain this further. So, again on the y axis you have mole fraction of monomer 1 in the copolymer, x axis mole fraction of monomer 1 in the co-monomer feed. So, now this is theoretically what you can do is that your R2 value you keep constant at 0.5, and all these graphs are for different values of R1. So, you see R2 is 0.5, when R1 is 1, then you have kind of ideal copolymerization behavior, of course close to being. So, this is like this. So, R2 is 0.5 and this R1 is say 2 here, R1 is 2 and R2 is 0.5. So, the multiplication is actually 1. So, this is your ideal copolymerization behavior we talked about. So, as the R1 starts to become lower, this graph starts to become closer to this linear curve, and when R1 goes below 1, what will happen is that you have the curve going like this. Now, remember when you are joining this 0 and 1, this linear graph, that indicates capital F1 equals to small f1. So, whatever points are there, that indicates the composition of the copolymer is equal to the composition of the comonomer. Now, when your R1 has gone below 1, what is happening is that, remember your R2 is constant at 0.5. So, if R1 keeps decreasing, then this multiplication is becoming closer and closer to 0. So, when your R1 has gone below 1, the value of R1, then your curve goes like this, it somewhere it will always cross this straight line of capital F1 equals to small f1. So, you can see that this graph is for R1 equals to 0.5, this is crossing here this straight line which is for capital F1 equals to small f1, which actually indicates, this line actually indicates all the points correspond to your copolymer composition is equal to the co-monomer composition. So, in your real situation, if your R1 is 0.5 and if it is going like this, if it is crossing your capital F1 equals to small f1 curve. So, at this point, this is the point where you will have a situation where your copolymer composition and the co-monomer feed composition are the same. So, this is the point. So, if you take a composition of the co-monomer that corresponds to this particular point, then what will happen is that this co-monomer feed will go into the copolymer with the composition remaining unchanged. So, when the copolymer is forming from the co-monomer mixture, the composition remains unchanged. Whatever composition you took in the co-monomer mixture, it goes directly into the copolymer formed. But when you are saying whatever composition, that composition is dictated by that particular point when you take that composition. So, this is called azeotropic copolymerization. So, when you are talking about azeotrope, a certain ratio of the liquids that goes into the vapor state and the vapor state composition does not change at all, that is your azeotropic distillation. So, same way this is also azeotropic copolymerization. So, if you look at the condition for azeotropic copolymerization, it is like this. Say you are taking this particular equation for instantaneous copolymerization. So, dm1 divided by dm2, that will be equal to m1 by m2, because this is the ratio at which you are taking your comonomer feed. The same composition will be maintained in the copolymer. So, this ratio will then become equal to this. This is the condition for azeotropic copolymerization, and if you elaborate this particular thing, it will become equal to, you have this expression of dm1 divided by dm2 somewhere here that I had drawn, that will be this expression. So, you equate this expression equals to m1 divided by m2. So, if you equate this expression with that, then what you will get is m1 divided by m2 equals to r2 minus 1 divided by r1 minus 1, or f1 equals to 1 minus r2 divided by 2 minus r1 minus r2. This you can derive separately. So, that means if both r1, that means if both r1 and r2 value are less than 1, then there is a condition for azeotropic copolymerization, and that condition will only be satisfied when you take the mole fraction of monomer 1 equal to this value dictated by this value. If you take the mole fraction of monomer 1 as this, rest of the thing is your monomer 2, 1 minus f1 is your f2. So, if you take this value, this mole fraction for monomer 1, then that particular composition when you are copolymerizing, that particular composition of the co-monomer feed when you are copolymerizing, your copolymer composition will remain exactly the same as the co-monomer composition. So, this is your azeotropic copolymerization. Remember, both R1 and R2 values have to be less than 1. Otherwise, that curve of the composition that we had, capital F1 versus small f1, that curve will never cross that capital F1 equals to small f1 straight line, which indicates that line, whatever point is there on that line indicates composition of the copolymer is equal to the composition of the comonomer mixture. Okay. Now, next what we want to talk about is copolymer composition as a function of conversion. Now, we are basically talking about all this instantaneous copolymer composition that we are saying is at a very low conversion. I have already talked about that. So, the co-monomer feed composition remains relatively unchanged under this situation, but what happens in real scenario? You keep on doing the copolymerization, conversion proceeds. Now, if one of the monomers is more reactive, it is continuously going more into the copolymer. As I told you, if you have an ideal copolymerization, your R1 R2 equals to 1, suppose R1 is 10, R2 is 0.1, then more and more of monomer 1 is going into the copolymer. We were already now, until now we were satisfied with the instantaneous copolymer composition, that means a very small conversion, small percent conversion from your comonomer mixture, that is all. Now, the question is what happens as the conversion goes on? This is a valid question, because if more and more monomer 1 is going into the copolymer, then your co-monomer mixture, which had a certain feed to start with, certain mole ratio of monomer 1 and monomer 2 to start with, this becomes poorer in content of monomer 1, because monomer 1 is going into the copolymer. So, it becomes richer in content with respect to monomer 2. So, that means your co-monomer composition is drifting with conversion. So, if the co-monomer composition drifts with conversion, correspondingly then your copolymer composition will also drift with conversion. So, you need then to understand how the copolymer composition changes with conversion, you need some expressions for that, which is not provided by your instantaneous copolymer composition equation, which we have been discussing until now. I hope this concept is clear with this. Now, let us try to do an analysis as far as that is concerned. So, let me write it down like this. So, as the degree of conversion goes up, as it proceeds towards higher degree of conversion, your co-monomer feed composition drifts towards less reactive monomer. We have already explained this. So, let us say you have a total of m moles of two monomers. You are starting with a total of m moles of two monomers, monomers M1 and M2, and your capital F1 is the mole fraction of the monomer 1 that has gone into the copolymer. We are talking about instantaneous copolymer composition, and let us say your monomer 1 is more reactive, then your capital F1 will be greater than small f1, because more monomer 1 is now present with respect to the in the copolymer with respect to what is there in the monomer. So, your copolymer actually richer in monomer 1 than your monomer feed. So, this means copolymer richer in M1 than feed. Okay. If you see the composition, your copolymer is richer in M1 than feed. So, your mole fraction of monomer 1 in copolymer is higher than mole fraction of monomer 1 in the co-monomer feed. So, let us say dm is the number of moles of monomer that has been copolymerized, total number of moles of monomer, both the monomers have been copolymerized. So, dm is the total number of moles of monomer. So, the polymer, so what is the number of moles of monomer 1 present in polymer now? It is F1 dm, because dm moles have been converted, total of dm moles have been converted, and F1 is the mole fraction of the monomer 1 in the copolymer. So, capital F1 dm is the number of moles of monomer 1 in polymer. So, what is the number of moles of monomer 1 in the co-monomer feed now? That will be m minus dm into small f1 minus small df1. This is the number of moles of monomer 1 in the co-monomer feed. So, if you do a material balance, then mf1 was the number of moles to start with for the monomer 1 in the co-monomer feed, and now you have this many number of moles present in the co-monomer feed. So, this subtraction will be equal to the number of moles of the monomer present in the copolymer. So, if you do the, so you know you have, if you just elaborate this thing, your dm df1 that will be cancelled, because these are two small terms, and then ultimately if you rearrange you will get something like this. Okay. Now, if you integrate from initial concentration of m0 to the final concentration of m, to the initial value of m0 to the final value of m, initial value, this is the number of moles, not the concentration. So, dm by m will be equal to ln m by m0, that will be equal to integral small f1 0 to small f1, that means small f1 0 is the initial value of f1 and the final value of f1. So, this will be df1 divided by capital F1 minus small f1. Now, capital F1, already we know that capital F1 is nothing but R1 F1 square plus 2 plus F1 F2 by R1 F1 square plus 2 F1 F2 plus R2 F2 square. So, basically capital F1 can be calculated as a function of F1, small f1, because small f2 is equals to 1 minus f1. So, this capital F1 can be replaced here, and this m by m0 is related to conversion, because conversion is nothing but m0 minus m by m0. So, then as a function of conversion we can actually find out from this particular equation the variation in both the comonomer feed composition as well as the variation in the copolymer composition. So, this then gives you the overall idea about what is the composition of the copolymer as a function of conversion. Okay. So, that explains then we are now trying to understand little bit in a deeper way how the copolymer composition changes. As you understand the logical way of that lecture, it goes from instantaneous copolymer composition, very small conversion, to the question, if you do the conversion continuously, the conversion goes to higher and higher value, how the copolymer composition changes. It is not the same as your instantaneous copolymer composition, because the composition might drift also. In order to know the system better, you have to actually have an idea of this drift, which system is becoming richer with what. If your monomer feed mixture is becoming richer with one of the monomers, how does that affect your copolymer mixture, I mean the copolymer composition with time. Those things you need to know, otherwise you do not know everything about your system. So, I hope that has explained this thing in little bit detail. Now, the next question that we want to consider here is the following. We have been talking about this R1 and R2 quite a lot, and they seem to be very important going by what I have been telling you, the reactivity ratios of monomer 1 and monomer 2. But I did not tell you about how to determine experimentally these values. So, let us say we are trying to have an analysis towards that direction. Now, we will start with this instantaneous copolymer composition, this expression dm1 divided by dm2 equals to m1 into r1 m1 plus m2 divided by m2 into m1 plus r2 m2. Now, this particular expression, if you do the rearrangement, you can write it down like this. I am not doing the full analysis, you can work it out by yourself. R2 is equals to m1 divided by m2 into dm1, or actually this dm2 goes here. So, dm2 divided by dm1 into 1 plus r1 m1 divided by m2 minus 1. So, this is the expression of R2 here. So, what you can do is that your R2 and R1 are linear in this particular expression. So, you can plot your what you start with is you do several experiments, and each experiment that you do, you start with a specific co-monomer feed. So, you know the value of m1 by m2, this is your co-monomer feed composition, and then after doing the reaction for a slight extent of conversion, say less than 5%, you analyze your copolymer composition, and then that will give you your dm2 by dm1. You can directly analyze the copolymer composition. Now, so copolymer composition analyzed. So, in this particular equation, other than R1 you know then everything. So, these two are linearly related. So, what you do then, you plot for each experiment, you plot R2 as a function of various assumed values of R1. So, you get a straight line. Now, you do another experiment where you change the comonomer feed and correspondingly you see you get another copolymer composition, and then again you put in this equation, and then again you plot R2 as a function of various values of R1. So, all these lines that you will get, the intersection of these lines will give you the best values of R1 and R2. That is how you can determine the values of R1 and R2 from this particular system. So, you start with a particular comonomer monomer feed composition and you do the reaction to less than 5% conversion, you analyze the copolymer feed, sorry, you analyze the copolymer. When you say feed, you are talking about co-monomer feed composition. So, you analyze the copolymer and then you fit in this equation. So, your R2 is linear with R1 and you put various assumed values of R1. So, you have a straight line. Accordingly, you generate several such straight lines when you are putting different values of, to start with, when you are saying you are starting with a different co-monomer feed. So, you will get corresponding copolymer composition and you get another straight line. So many straight lines will come and then the best fit values of R1 and R2, the best values of R1 and R2 will be the intersection of these lines. So, that will be the best values of R1 and R2. Now, what I will go into in the next class is to talk about the microstructure of the copolymer. So, what do we mean by microstructure of copolymer? We have already talked in detail about copolymer composition. We talked about the instantaneous copolymer composition, we talked about the co-monomer composition feed, and we said that instantaneous is not enough. We have to understand how with conversion the copolymer composition is changing. So, we understood that also in terms of the equations and all, and then we have experimentally determined R1 and R2. So, what else remains to be known? Something very important that we have not talked about is what we call as microstructure. So, okay, we know you have a system. So, your system may not be your, when you are saying ideal copolymerization, it may not be R1 R2 equals to 1 means it may not be R1 equals to 1 equals to R2. It may be R2 some value and R1 some value, say R1 is 10, R2 is 0.1, that is my pet value that I have already talked about and I have explained all the things with that. Or maybe you have an alternating copolymerization where R1 and R2 both are not equal to 0, but they are less than 1, or one of them is higher than 1, one of them is lower than 1. So, the question then is, what is the sequence length distribution? Suppose your M1 has gone into the polymer and M2 has gone into the polymer, the two monomers. Now, they are distributed. Let us say you are talking about a random copolymer, let us say you are talking about an ideal copolymerization, R1 and R2 are not equals to 1, they have some different values, R1 greater than 1, R2 less than 1. Then the question is, of course, say M1 which is more reactive, it will go in more proportion to the copolymer, but both of them will be placed in random placement. So, what I would like to ask here is, let us say you are talking about a triad M1, M1, M1. When you say triad, that means say this M1, M1, M1 unit, both sides there are M2. So, this is a separate M1, M1, M1 unit in the copolymer. How many such M1, M1, M1 units are there? In other ways, what is the number distribution of these M1, M1, M1 units? What is the probability that we will have an M1, M1, M1 unit? Or the same way, what is the probability we will have a pentad M1, 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 or a dyad say M1, M1. We can talk about M1 like this, we could talk about M2 also like this. So, even in random placement, they will have different proportions like this because the reactivities are different. So, if you are talking about a dyad say M1, M1 or say M2, M2, what is the distribution, number distribution, how many such dyads are there of M1 in the whole polymer chain on an average? How many triads are there, how many tetrads are there, how many n units consecutively together flanked by the other monomer both sides are there? This gives you the complete understanding of your copolymer composition, and that is what is necessary, and that is why it is necessary to talk about what you call as microstructure, or in specific terms sequence length distribution. So, this is precisely the thing that we are going to talk about in the next class. Until then, thank you and goodbye.